Good morning, welcome back to energy conservation and waste heat recovery. Today we are going to continue our discussion on energy economics, and last class we got introduced to the concept of LCOE, which is levelized cost of energy. Okay. We were looking at the definition of from the UK government, which said that it is the net present value of the total installation and operating costs of a generic plant over the net present value of the electricity generated over its operating cycle, okay, or over its operating life. So, today what we will do is we are going to look at some of the definitions of or how do we write LCOE. So, LCOE can in very simple terms I can write LCOE in this manner. It is a ratio, it is the cost of generating 1 kilowatt hour of electricity. Okay. So, in the numerator we have to write down the costs, and let us say the life cycle goes from 1 to n years, n is its useful life. So, I would write it as the initial installation cost. So, I would write it as IT, or I would rather write it I from 0 to 1, 0 to n, plus MT plus fuel FT, I will come to that what each of these means, divided by 1 plus R to the power T. Recall from our discussion on net present value, R is the discount rate, and in the denominator I will write the net present value of the total electricity that is generated, and this is also going from 0 to n. I would write ET divided by 1 plus R to the power T. Okay. So, this is a very simple expression for LCOE. Okay. Again, let me write down what is I. I is initial cost, initial investment, which typically is at the 0th year. M is maintenance and operation and maintenance. Also, I would say it can be written as AO, operation and maintenance, let us say, and F is fuel, okay, and these two together is annual operating cost, AO. Okay. And what is E? E is the energy generated, and here also we have to put a discounting to get net present value of the energy that is going to be generated, let us say 5 years later. So, today if I have to do this, this is how I am going to calculate LCOE. Yeah. So, this is, I would say, rather a simple definition. So, which does take into account several of these metrics. So, for example, now if you look at this, let us talk about a natural gas or a natural gas plant. Okay. I would need fuel. So, this F is going to be a significant amount in subsequent years. Initial investment cost will be there, but when compared to a solar plant, this I is going to be very high, but F is going to be low, right. Remember, this I have put it as IT, which is investment that we are making every year, but every year this is going to be not valid. Most likely it is not going to be that valid unless you keep on adding features to your plant over its life, or at least for the first few years of its life. But typically I will have a significant value at t equal to 0 and probably nothing significant after that. Only exception is, as I said, if you want to keep adding features or scaling up your plant over the years, then of course I will have some value in year 1, 2, 3, 4, 5 and so on. Clear? So, this is one way. So, what is the unit here? If I look at the unit, The upper one is cost. So, this is going to be dollars or rupees or whatever, and the lower one denominator is going to be kilowatt hour. This is the unit of LCOE. It is dollars per kilowatt hour or dollars per megawatt hour, or depends on the location. It can be pounds per kilowatt hour, it can be rupees per kilowatt hour, and so on. We can look at a more complex definition of LCOE as well. Okay. And that is also there. Okay. Let me first write it down and then try to explain each of this. So, I would first write the numerator, and I would say I minus sigma, again R, not R, sorry, T 1 to n, depreciation divided by 1 plus R to the power T times tax rate. I will come to what each of these mean, plus sigma, again T 1 to n LP 1 plus R to the power T minus sigma 1 to n INT or interest times TR 1 plus R to the power n, okay, plus, I am sorry, I am running out of space. I will continue the numerator over here at the bottom. I am sorry, this is going to come here, plus sigma, again T 1 to n, annual operating cost 1 plus R to the power n, and then minus salvage value 1 plus R to the power n. And what is going to be the denominator? Again T 1 to n initial kilowatt hour times 1 minus system degradation divided by 1 plus R to the power n. Okay. So, I am sorry, this is a little complicated, but let me again write it down, or let me again spell out each of these terms so that you can follow. The first term is I, and we know that is initial investment. Or installation cost. The second one, I would write it down, DEP is called depreciation. So, now every asset, in this case this plant, the equipments, etc., they are going to depreciate with time. The value of what it is today is not going to be the same. Of course, an old product sells for less than a new product, we know that, because there is a depreciation. Okay. So, what happens is a business can claim a tax rebate due to this depreciation. The tax rules, tax laws allow for that. Okay. So, therefore, if I show that my equipment has depreciated by this value, I can claim a tax rebate on that. Okay. So, that has to be subtracted because that is a cash inflow. So, TR stands for tax rate. Let us say for building this plant, for building this installation, I have taken a loan which I am repaying. It is a debt or a loan. So, it is a loan payment, LP is loan payment, which I have to pay the monthly installments to the bank or the yearly installments to the bank. Clear? Now, out of this loan payment, I will get some tax rebate because of the interest that I pay as part of my loan payment. Clear? So, for example, as individuals we get a tax rebate because of interest that we pay on our housing loan. So, similarly here also the businesses are allowed to claim a tax rebate because of the interest they pay on loan payments. AO we know is operating cost, annual operating cost. SV salvage value. This is what I am going to get, is an inflow at the end of n years, and R is the discount rate. Okay. If you look at the denominator, what I have written is initial kilowatt hours. So, this is the rating of the plant, but the plant is going to degrade with time. Okay. So, today if my plant, let us say, gives x gigawatt hour over a period of 1 year, after 5 years it is going to be maybe only 80% of that, because the system has degraded, equipments do degrade. Okay. So, therefore, the production that I am getting after 5 years or after any number of years is going to be less because of system degradation. So, that has been taken into account. So, when you add up the energy that is generated, and again remember, I do not have this data, I am trying to calculate an LCOE today to make sure what is going to be the cost of energy for the plant that I am proposing to build. So, I do not have this data, I am going to assume something and then calculate it in this manner. Clear? So, LCOE calculation can take into account a variety of stuff like this. So, this is, I would say, a little complex in the sense that it kind of encompasses a lot more elements, right. Compare that with a very simple one that we wrote. Clear? Both of these are valid. Okay. So, what is it that I am trying to say? By showing you these two different definitions of LCOE, the point that I am trying to drive home is, yes, LCOE is a very good metric, it is a level playing field to compare different energy installations using different sources of energy. Of course, all that is given and valid, but before comparing LCOE, it is very, very important also to keep in mind, to know that how was the LCOE calculated, what are the factors that went into the LCOE calculation. If somebody comes and says and takes into account all this, the depreciation, the interest, all these, and it will show that my cost is actually less, it does not take into account system degradation. So, that is one way. The other guy may come and say, and he just uses a simple formula, he does not take into account his depreciation, he does not take the tax rebate due to interest on loan payment, he just shows the loan payment and he says that the cost is going to be high. He also says that my system is going to degrade with time. So, he is being very honest, he is going to being very fair, and he is considering all this. Now, is it fair to compare these two LCOEs that have been calculated completely in different terms using different factors? No. So, the point that I am trying to drive over here is, it is important to know that how the LCOE has been calculated. So, important to ensure that LCOE calculation method is identical before comparing values. Okay. And example, as I said, was thinking of factors, for example, depreciation, loan payment, interest, degradation, all these are there. One can also say that I am going to put in tax credits, for renewable energy, for solar, for wind, some governments gives you tax credits, tax credit. It is not a discount or that you get because you are paying interest. It's just that the fact that you are putting up so people who put up a solar panel, let's say in California, they get a rebate on their electricity bill. Okay. What else? The choice of R, right, discount rate. This can be arbitrary, this can be subjective, and can play a huge role in altering the value of your LCOE. Okay. So, all this need to be kept into account, right. So, now if I write electrical energy times LCOE is equal to lifetime cost, right. So, what is this going to be? This is going to be in kilowatt hour or megawatt hour. This is going to be dollars per kilowatt hour, and this is going to be dollar, right. Again, keep in mind this is discounted, this is also discounted. Clear? All right. So, if you look at this and I say that this is a power plant that I own today and we are generating electricity which I am selling to customers, how much am I going to charge? Okay. So, LCOE can also be thought about as the minimum cost of electricity that I can charge to my customer to make this plant economically viable, to make this plant, I will not say even profitable, to make this plant non-loss making or not a losing proposition, right. So, if I look at this, this is my revenue. If revenue is equal to cost, then I am break even. Greater than cost, profit. Less than cost is loss. So, therefore, as I said, LCOE, you can also think of it as LCOE is the minimum average cost of energy, of course, that one can charge so that revenues earned by selling energy is equal to the cost of producing or generating the energy, right. We looked at various factors. We looked at initial cost, right. What all did we look at? We looked at, if you look at revenues and versus costs. So, here I would write installation cost, which also includes equipment, labor, everything, plus ongoing costs. Which is operations, maintenance, fuel, debt or loan payment, tax, etc., etc., a lot of things, dividends, that you have to pay your shareholder, all that stuff if you are a company. Okay. What is the revenue? Revenue is your energy times price, this is kilowatt hour and this is dollars per kilowatt hour. Okay. And there can be other revenues also, plus let us say tax credit, carbon credits, etc., etc. Now, look at this. All this is for the future, and if you look at this, this is now or present, this is now, this is future. So, if this is future, this has to be discounted, right, the net present value method. You have to find the net present value by using the discount rate, right. So, the way I am showing this is here is again to drive home the point that all these can become part of your LCOE calculations. Okay. So, when we are comparing two installations, we have to make sure that the factors that have been incorporated while calculating LCOE must be the same for two LCOEs to be compared, okay, for the two installations. All right. So, that kind of brings us to an end of LCOE, and which kind of what we have done is we have finished another metric of energy economics. Okay. The last one that I am going to talk about today is something called input output analysis. Okay. We probably won't be able to finish it, but we will just introduce. This is a very classical method. This is not really a metric in the sense that it is not a term like LCOE, like it does not have a definition, it is not like a mathematical expression, it is a mathematical exercise, it is an analysis. Okay. So, before we start, its input output method is a very classical method in the field of economics. It was first proposed by a Nobel laureate economist. His name is Vasily Leontief. Vasily Leontief proposed this in 1950s, and it was, I would say that it is one of the first successful implementations of a mathematical model in macroeconomics. Okay. And as we will see as we go through this, the beauty of this method lies in its simplicity. Okay. It is very powerful, but it is very simple, and that is where the beauty lies. Okay. So, let us talk about it. If we think about a nation, let us take a step back, we think about a nation. Okay. Even in India, for example, a national economy is typically broken up into several sectors. So, India, for example, I think has 100 to 130 sectors. So, what can these sectors be? Sectors can be agriculture, transport, energy, banking, manufacturing, a lot of things. Okay. Even energy can be broken down into electricity, into coal, and so on. Information technology, so on and so forth. All right. So, if we think about these economic sectors, okay, and let us say I would write down national economy broken to several sectors, and let us talk about only one of those. Let us take just a few of them. Let us take let us say India, for example, and I would say I will take 4 such sectors: service, manufacturing, energy, because that is what we are talking about here, and since it is India, we will take agriculture. Okay. 4 major sectors. When we talk about service, we will talk about any service industry like banking, post office, so on. All right. If you look at this, all these sectors have outputs, but what is more important is a sector of output of all the sectors. Each, if you take any sector, the output of that sector goes as input to other sectors. For example, let us take agriculture. Okay. So, let me write down here what I just said, that first of all, output of all sectors contribute to economy. But more importantly, what I would like to say is the production or output of a sector, of any sector, is partially used up by the production process itself and other sectors. Okay. Let me underline this for some of the partially used up production process itself and other sectors. Okay. So, let us take into account agriculture. Okay. So, agriculture, for example, the output of this plays a major role in the Indian economy, we know that. Okay. But now, if you look at it, what goes into agriculture? Okay. First thing, does the output of energy goes into agriculture? Yes, because we need the agricultural machinery, we need the harvesters, we need the tractors, etc. And once the crop is harvested, we need to transport it to the market, finally to the end user. So, agriculture industry does need input from energy. Okay. And when we started our discussion in energy economics, we rather said that almost output of any sector or anything, production of anything requires energy. So, we will see that energy actually plays an input or is an input to almost all sectors. Okay. Does manufacturing form an input to agriculture? Of course, because all these tools, the harvesters, the machines, agricultural machinery are all produced by the manufacturing industry. Okay. What about service? Yeah, because the farmer may have to take up loan, they may have to borrow money for crops, for seeds. Okay. So, the service industry like banking does play a role and this forms an input to the agriculture sector. And what about agriculture itself? Yeah, of course, because part of the agricultural harvest or part of the agricultural output forms the seeds. Okay. All right. So, this is important. So, you can see that all this output of all the other sectors form input to the agricultural sector. Okay. And there are various other examples. Steel and automobiles are two different sectors, but steel, output of steel forms an input to automobile, right. For example, what else? Electricity goes to all sectors, also industries, but to the power plant itself. So, that is an example of electricity that is generated in the power plant is used in the power plant itself as well as to the end user and to all other plants also. That is energy again. All right. So, this kind of tries to tell us that if we look at the economy and look at the different sectors of economy, the output of any sector is used up by some or all of the other sectors as well as by the sector itself, and then whatever is left after that is available for use by the consumers to meet their demands and also let us say for export. So, for example, agriculture industry, the crops or the harvest that we produce first has to feed the population, only after that can we think of exporting it. Okay. The energy that is produced has to first run the existing infrastructure, okay. And then it comes to the end user, and then finally we can think of selling energy to outside the country. Okay. All right. So, therefore, this is where we will stop today. We talked about the different sectors of an economy and how they are interdependent on each other. In the next class, we will talk in more details, and we will take up a specific example to show what is the input output analysis that was proposed by Vasily Leontief. Okay. Thank you very much. Have a great day.